Now, the next theorem we have is intermediate value theorem. And this theorem really concerns all continuous functions. In particular, we're going to look at polynomial functions. The polynomial functions are always going to be continuous. And this theorem is really useful, so let's look at it first. If I have a continuous function, and it could be on any interval, but say for example in particular it's continuous on interval from a to b. And if we know that the values of my function are different at a and at b, so say f of a is one value, f of b is a different value. What the intermediate theorem tells us is that the function f will assume all of the values y in between f of a and f of b, as x varies from a to b. And I mean, you can kind of think of it in terms of how could it fail, right? If my function was discontinuous and I had an interval from a to b, so this is my f, how could it fail? If I have a value f of a here, f of b here, for any one value between f of a and f of b, for a continuous function, that means that if we go to the graph of the function, there will always be some value c between a and b that will produce that value y. If the function was discontinuous, say maybe I have something like this, then this would no longer be true, right? So if I take some value, say L, in between f of a and f of b, and try to go to the graph of my function, I'll find nothing. There's no value x that will generate the particular value y. Right? But for continuous functions, we can always be sure that this will be true. And in general, this would, at least for polynomials, when we start looking for zeros of polynomial functions, this would be a very useful theorem. And the way you would use it for zeros is, well, at least in one example, say if I have some interval from a to b, and I evaluate my function at the endpoints. Alright, so say I take value x equals to a, evaluate my function equals to f of a, and my f of a happens to be less than 0. And then I take a value of x equals to b, evaluate my function value is f of b, and f of b happens to be greater than 0. So because f of a is less than 0 and f of b is greater than 0, by intermediate value theorem, any value y I take on the y-axis that's between this negative value f of a and this positive value f of b, any value of y I take, I should be able to find the value x in a b that will produce this value y. And for zeros, we're usually looking for values x, which would produce a value y equals to 0. So if the function is continuous, that means that I would always be able to find a value x in a b so that f of x equals to 0. So it's one way to kind of look at the function values at different points, and using the fact that the function is continuous, you'd be guaranteed that you will have at least one 0 in between a and b. Right, and you can go in opposite direction, like if f of a was positive and f of b was negative, then that would mean that somewhere I must cross x-axis in order to get to b and f of b. So I should have at least one 0 on my interval. So we're not going to apply it too much directly, because in general you would just have to do it computationally, and we want to kind of look for zeros exactly. And how do we look for zeros? So in general, there isn't really one way to go about this. The easiest way is to try to factor a polynomial, and if you can, then each one of the factors will correspond to 0. But sometimes it's not really that easy to do. So for example, if I have f of x equals to 6x cubed minus 19x squared plus 16x minus 4, if you try and factor it, you're going to get a little bit stuck, all right? But maybe you tried some different x values, plugging it into your f of x, and somehow you accidentally picked the right value, so you guessed that x equals to 2. You plug it into your function, and, well, that's nice, it works out. So x equals to 2 is actually a 0 of the function f of x. And we know that zeros correspond to factors, so a 0 x equals to 2 corresponds to a factor x minus 2. So what does this mean? Well, this means that this particular function f of x, I can also write this as f of x equals to x minus 2 multiplied by some unknown polynomial, right? Which would also consist of some factors, but I don't really know what those factors are yet. And how do we find these factors? And if you look at this, okay, if I have f of x equals to something multiplied by something else, how do I solve for this something else? And in general, we can still do division, right? If I divide f of x by x minus 2, I will end up with x minus 2 multiplied by q of x divided by x minus 2. So this factor x minus 2 will cancel, and this will give me that unknown polynomial q of x. Now, so this is why we need to learn how to divide not just numbers, but divide variable expression. And in this example, we're going to divide polynomials. There is a couple ways to do this. So one way that works for all polynomials is called the long division of polynomials, which would be very similar to long division of numbers, but we'll just have to kind of practice and figure out how to do it so you can do it pretty quickly. We will have another way to do division of polynomials, but it would only work for division by linear factors. But let's do the long division first, because it's the most general way to do this. And you don't just have to divide by linear factors, you can divide any order polynomial by any other polynomial of degree the same or less than that. And so let's look at the example we were talking about earlier and try to divide this to find our unknown q of x. Because this would help us basically factor and find all of the zeros of this polynomial function. Because if I find this q of x, f of x is polynomial of degree 3. X minus 2 is polynomial of degree 1. To get polynomial of degree 3, I will have to multiply polynomial of degree 1 times polynomial of degree 2. And polynomials of degree 2 are easy to deal with, right? Even if I can't factor it, I can always just find zeros by using the quadratic formula. So let's do this. Basically, we need to figure out how to divide this third order polynomial by this first order polynomial.